Everyone, welcome back to Math 256. This is Scott. Let's get started. So, up till now, we have been talking a lot about systems, but we have said precious little about how to solve any of these systems. Well, what we're going to start now is a project of figuring out how to actually solve the systems that we can solve analytically. And that starts here with 2.4, where we start the task of solving systems analytically, and this is just going to be it's just going to be one particular subclass, but anything anything we can do to get the ball rolling. All right, so here's the setup. So what we are going to be focusing on to begin with is a category of what are called partially coupled systems. So, so partially coupled system. And what this refers to is the fact that one of the variables may depend on the other, but the other stands alone. So basically the setup here is the x dt is just going to be equal to some function of x, whereas dy dt is going to be a function of x and y. Or perhaps it's the other way around. Maybe dx dt is equal to f of x comma y, and then dy dt is just going to equal g of y. So in other words, one out of these two equations is free of the other variable. So specifically, so these are the two possibilities. So here, just so it's clear, are the what are the components here of the or, so of the disjunction? It's that versus that. So one of the two equations is free of one of the variables. So that's what it means to be partially coupled. So if both dy dx and dx, or sorry, both dx dt and dy dt involved both variables, then it would be fully coupled. Like the two variables would be intimately coupled with each other. Here, at least one of them is independent of the other. So here's the basic idea for how to do this. So solve the one that is free of the other variable. So solve the equation that only involves one variable. And then that will usually be able to, then we can plug that solution in to the other equation, and hopefully we'll be able to get somewhere with that. Then plug that solution into the other equation, and hope for the best, and solve using one of our pre-existing techniques. Okay, so here's a tool that will come in handy. since we are going to be pretty much exclusively focusing on situations where the functions are linear, here's a tool for a specific category of functions. So this is equations of the form dx dt is equal to just alpha x. So just something of this form where it's just a constant coefficient. So here, this is separable technically, and if we were to do the separation of variables, we would get that x of t is equal to c e to the alpha, alpha t, which which you can do this by doing separation of variables, and that's a whole well and good, but you can also kind of see this directly by just validating that if you were to take the derivative of this, what would happen? The alpha would come down in front, and that would be basically reproducing this equation or this formula, but with an extra alpha in front, exactly as the differential equation foretold. So that's the tool that we will use here, and then what will happen is we are going to end up with something where we will usually be able to use one of our pre-existing techniques, and what that will often amount to is an integrating factor, as in for linear functions, or sorry, linear equations. Let's just roll up our sleeves and get to it. So as an example, so let's just say solve. The following systems. All right, well, here we go. Let's give it a try. A. So we'll start with x prime is equal to negative x, y prime is equal to x minus 3y. Okay, so here we can see it is partially coupled. The x prime equation has no reliance on y. That's what makes it partially coupled. Okay, well, to begin with, actually, let's just squeeze the solution, at least as far as x is concerned, right into this little space available. So for x, so dx dt is equal to negative x. That implies that x is equal to, I'll call it c1, e to the negative t. So this is just exactly in the same format as what we saw above, with alpha here being played by -1. Okay, so far so good. Nice and straightforward. Now, dy dt is equal to x, which I already know, c1 e to the negative t, minus 3y. Okay, well, so be it. And then if we were to rearrange this, we'd have dy dt plus 3y is equal to c1 e to the negative t, which is linear. So this is a linear first order ordinary differential equation, which then means that we will be able to find an integrating factor, and we will be able to solve it by means of that tool. So rho is equal to e to the power of the integral of 3. So here p is just equal to 3. Q is equal to c1 e to the negative t. Just to make it clear. Okay, so then rho is equal to e to the power of the integral of 3t dt, sorry, 3 dt, I should say. Anticipating here my own results. So then rho is equal to e to the 3t. Okay, so be it. Well, then I multiply everything by that rho. So rho y prime plus 3 rho y is equal to c1 e to the 3t e to the negative t, so I multiply by the row there. And on this side, notice then that rho prime would equal 3 times e to the 3t, which equals 3 rho. So that's nice. So that means then rho y prime plus rho prime y equals c1 e to the 2t, which is all exactly the way things are supposed to work when we have linear differential equations like this. What we see on the left is exactly the expression that you'd get if you were to do the product rule, and in particular if you were to do the product rule on rho times y. So in other words, we have this, and then we would take the integral of both sides, which is of course then going to be 1/2 c1 e to the 2t plus c2. So we've got now a second constant, and we'll multiply by 1 over rho here to divide that. In other words, and here actually I might as well put in what rho was. It was e to the 3ty. So then I'll multiply both sides by e to the negative 3t to cancel it. So then y equals 1/2 c1. Looks like it's going to be a net of e to the negative t. So it's going to be negative 3t times e to the 2t. So that'll make negative t, and then plus c2 e to the negative 3t. So then our solution. So then our solution here just looks like x equals c1 e to the negative t, y equals, and I want to keep actually the same c1 here as I had before, because the c1s of these two equations are in fact representing the same number. So I wouldn't want to exercise any liberty here in renaming my c1, because whatever the c1 is for the x, that is the same c1 as appearing down here for the y. So whenever I get initial conditions, I'll be able to coordinate these two expressions with each other. So that's a solution, and that's how we do that. So it's kind of a rundown of all of the methods that we have had in play. Well, not all of them, but a lot of them. We had a separable equation, we had a linear equation, and we have now a system of equations as well. But let's try another one. So this time, the one that will be coupled will be the y, or sorry, the x. The one that will be uncoupled will be the y. So what that means is we'll have x prime is equal to 3x plus 4y. Y prime is now just going to rely on the y. And again, we're just going to be using constant coefficients here, so we'll just have 3x plus 4y for the x, and y prime equals negative 2y. All right, well, let's start with what's easy, and that will be the y. So dy dt. This is going to equal just some constant times e to the negative 2t. All right, so be it. Well then, what does that mean? That means that dx dt, is going to be equal to 3 times our mystery x plus 4c1 e to the negative 2t. And once again, we have here a linear equation in x. So now we have dx dt minus 3x equals 4 c1 e to the negative 2t. And then what that means is that we can just once again announce what the p and the q and the rho will be. So p will be negative 3, so just a constant function. The q is going to be 4 c1 e to the negative 2t. And so then the integrating factor here is going to be rho, which is going to be equal to e to the power of the integral of negative 3 dt, which is e, in other words, to the negative 3t. So that is what we shall now multiply everything by, both terms of the left and the sole term of the right. All get multiplied by the rho. So what's that mean? That means then rho dx dt minus 3 times x, so 3 rho x, gotta multiply everything by, so 3 rho x is equal to rho for c1 e to the negative 2t. But let's remember here, rho is something specific. Rho here is equal to the e to the negative 3t, which means, by the way, for the record, rho prime negative 3 e to the negative 3t, in other words, negative 3 rho, which is, of course, always the purpose of the integrating factor. We always want the derivative of the integrating factor to be equal to p times the integrating factor. So then, what does that mean? That means you've got rho x prime plus rho prime x is equal to, and then over here we can just plug in what we actually have here. So we have 4 c1 e to the negative 5t is what would happen if I were to multiply rho by e to the negative 2t. So then that means rho x all prime 4 c1 e to the negative 5t. So now I take the integral of both sides, and that will undifferentiate the left, leaving me rho x 4 c1 e to the negative 5t dt. And now we can actually just restore the value of rho over here. So it's e to the negative 3t is equal to, how do I integrate this? So I'll just divide by the coefficient, so it'd be negative 4/5 c1 e to the negative 5t, plus c2, so our second constant of integration. And then I will just multiply both sides by e to the 3t in order to cancel that. And away we go. So that's going to be negative 4/5 c1 e to the negative 2t plus c2 e to the 3t. So then our solution. Our solution is y. Oh, sorry. Over way back here. I said dy dt, but I really meant just y. Obviously, I did not mean dy dt. That would have been just equal to negative 2y. Whoops. All right, back to work. So then our solution is that y equals c1 e to the negative 2t, and x is equal to negative 4/5 c1 e to the negative 2t plus c2 e to the 3t. All right, so this is how we can solve this relatively limited category of systems of differential equations, where we have specifically a partial coupling. So one of the two is uncoupled from the other variable. Just as a note, if we want C1 and C2, we would use initial conditions. All right. So like I said, this is a relatively limited category of differential equations. It's just something to get our feet wet. And now in the next section, we'll embark on what is going to be a more general procedure for more kinds of systems of differential equations. All right. So that'll be it for this little section. See you next time.